to the DAF Museum. Welcome partners, welcome friends, welcome family, and of course the people who are watching at home. First, some messages. Please turn off your phone, make sure it's off. And also, if you're going to get a drink after the presentation, keep the drinks in this area. You can walk through the museum and then keep your drinks, please, here. So, to begin. Jesse Koenders, team leader of University Racing Eindhoven, of this wonderful team that the presentation of their new car you are all attending tonight. So, I'll be your host for tonight, and I'll be guiding you through this evening. First of all, I will tell you something about the place that we are, the DAF Museum, and a little bit about the history of our team. I will guide you through our team, to the structure of our team and every team role, and then tell you something about our partners. After which, Torben, my colleague, will take over and tell you everything about the thing that you are coming here for tonight, a URE12 in technical matters. To begin, we are here in the DAF Museum. And as some of you may know, DAF, in the history in Eindhoven, was already a very company full of pioneers. They made a continuously variable transmission, a CVT, that made sure that the car that you see here had the same top speed going forward as going backward. And also making sure that the engine that is in this car is always used perfectly, is always in its optimal RPM range. Well, always using an engine optimal, that would of course be very interesting in a race car. And as you might expect, a race car from Eindhoven is orange. Here you see the DAF Formula 3 car of 1968, also using this CVT. And here you see our URE11 next to it, upstairs. As you see, the automotive engineering in Eindhoven, 50 years apart, with the Formula 3 car and our last car from 2016. Starting with a tubular frame and a combustion engine in the back, a rear-wheel drive car, going to a carbon fiber monocoque, a full carbon fiber lightweight chassis, full aerodynamic package, and 4 in-wheel electric motors. But of course, we did not get here in just 1 year. We have a long history of University Racing Eindhoven, and I will guide you through this by starting with our beginning. A few engineers from the Eindhoven University of Technology were enthusiastic about cars, and they wanted something more than their lectures. They wanted to join the renowned Formula student competition. I will tell you more about this competition later, but they had a dream to compete there. And at the first, they didn't want to join the competition, but really think, can we build such a thing? Can we build a car? And they tried and started with this soapbox. A soapbox created by those young engineers that allowed them to see that they could actually build something with the things they learned in their lectures and apply the theory into practice. Well, of course, you can see here, it has 450 bricks of weight, 2 manpower of propulsion, and an aerodynamic package, a rear wing, which we will see very later in our history. So a lot of cars have been built without the rear wing after this one. After this, a few years later, they did it. They competed in the Formula Student competition with this car in 2006. As you see, it's very different from the cars that you have seen when you walked into this museum that are also from URE. It's an earlier stage, and it looks more or less like the car from DAF, the F3 car. It also has a tubular frame, which makes it a bit heavy, 280 kilograms. It goes from 0 to 100 in 4.2 seconds and is propelled by a 4-cylinder combustion engine in the back, so also a rear-wheel drive car. But you know we are also building electric cars since 2010. We made a step towards the electric competition once the competition allowed an electric drivetrain to participate. And with the very first electric race car in the Benelux, we created the URE12 that you see here. It's a bit lighter than the previous car, which is 269 kilograms. You might think, why is it lighter? Well, an electric car, really back then, had a battery package, and a full electric drivetrain is heavier than a combustion drivetrain. So it's only a bit lighter, but it's actually a lot of an achievement to obtain this. Also, the acceleration has increased, 3.8 seconds, because of the direct torque of the electric motors in the back. And I said two electric motors, because there are already 2 motors in the back to make sure that we can apply torque on the rear wheels in different matters during cornering, making sure we can go faster than our competition. And it did. It won the competition in Austria. And a fun fact, it's currently based in Austria as well, in a museum, together with this Formula 1 car. Well, this car still looks very different from the car that we have today. We made a big step in 2015. In 2015, we went back to a blank sheet. We used several simulation software that we created ourselves to determine the perfect parameters of the car. How big is it? How much does it weigh? How much power has it? And those simulations resulted in a concept, the URE10. This URE10 actually won the competition in Formula Student United Kingdom of Class 2, the concept class, where it is supported that we use the right way to determine the perfect Formula Student race car. And it has a very different performance than the car that I showed you earlier. It is 196 kilograms due to full carbon fiber chassis and aerodynamics. It goes from 0 to 100 in 2.4 seconds, 4 in-wheel electric motors, of course, and finally, again, since the soapbox and aerodynamic package. So, you now know a bit about the history of University Racing Eindhoven, but of course there's a team behind it. A team, a group of people who are actually building, designing, and racing this car. And here they are. 62 members of the team, all working towards the same goal, to make the ultimate Formula Student race car. Every member has his own job, with 5 team members working full-time, doing everything and making their study on a pass. And next to it have all the part-timers work next to their studies. So this team is, of course, with 62 people, a structure is needed. We need to make sure that everything runs smoothly within the team. And that is why I'm going to show you this structure with this diagram. So, at the beginning, like I explained, the board. 5 people who are working and have their studies on a break, work everything on the car, and manage everything. Every manager has a group of people beneath them, so a certain responsibility. With the first being responsible for the aerodynamics and chassis, the second being responsible for vehicle dynamics, the third being responsible for operations, public relations, one who is responsible for electronics, software, and control, and finally, powertrain and testing. And especially the last one, testing, is a very important thing in Formula Student. We are making prototype cars which build up from the ground. We need to test everything to make sure that it works during these races. And this year, we tested over 400 kilometers with our previous car to make sure that all our systems that we designed for the new car are already thoroughly tested and can directly be applied on the URE12 that you will see tonight. Above our team, there's an advisory commission of alumni of the team. Team members who are now doing a PhD at our university and helping us guide through different difficult decisions. And above that, there's an advisory board of experts working at the theory, all with a certain expertise of the car. But for now, let's focus on the team, our team. And how better to explain how it is to be a part-time member of our team than to show Josh. Josh is a first-year electrical engineering student who has the first year at the team this time. And he will show you what it's like to be a part of our team. So, please, here's Josh.
My name is Josh Klaassen. I'm a first year electrical engineer. I'll be part of the electronics department, and this year I'll be designing the wiring harness of the URE12. I hope to expand my knowledge on electronics and get a better insight of the workings of the electronics in the car. During the introduction week, URE organized a workshop where I came in contact with the team, and after the workshop I immediately decided to join the team. We are now 3 months into the design process. So far I've mainly been working on the connector table, an Excel sheet containing information on how the wires run inside the car. I started the design process by analyzing the connector table of last year. After that I discussed the changes with respect to last year with my team members, and based on that I started designing my own version. During these meetings we discussed progress and any possible problems. The problems I encountered during my design process were discussed with an experienced team member, which resulted in quick progress. During my 3 months here at URE, I gathered a lot of information about the car and the electronics in it. All electrical components are connected to the wiring harness, which gives me a better overview of the complete car. We use a detailed planning so we can see when the design phase of different parts is finished and when the production starts. Currently I'm working on the wiring harness. It's a really nice way to put the theory into practice. This was my first year at URE, but definitely not my last.
So, the sponsoring has been starting already quite well. The field of the of industry we are working is widespread. It's in 50 countries all over the world, and has a relationship to shipbuilding and also to the industry, taking care that casualties and problems with fire, water ingress and so on are a thing of the past. So they call me here president. Of course, our company is not American and it's not big. It comes from the Achterhoek in the Netherlands, so it's more a farmer's country than anything else. Anyway, compared to what is going around here, we have seen that our presence worldwide is overwhelming and is necessary. We have our customers in a wide variety of applications, even up to the nuclear industry, naval vessels, and so on. So it's another matter of technology, but it's valuable. With that aspect in mind, different a little bit from here, but in fact almost a similarity, because of the field of where we are working in and taking care of customers so that, and also the public, that safety is written sky high, we have to contribute all the time with ideas how to solve this. And of course, this is also not an easy matter. So we have also a group of young engineers around working in the same style as what they are doing here to make the world a little bit safer. Different with this, and that makes us a little bit easier to handle, is that in our company, the shop floor to the management is just one level. So it's easy to work on, and the members in our team have a lot of freedom there. So the reason for sponsoring here is to see what is going around here with the management and how are they going around with the development in their machines here compared to what we are doing in our field, how that fits together. So what we have seen, and that is one of the things we have in our company, a young group of engineers, of which one is here tonight, having the freedom to develop and to make the mistakes. What is the route to success is generally enthusiasm. It's passion to do it. There is commitment. You have to say, okay, this is my thing and I want to be a part of it. You have to put your energy on it. Now, that's what we see here also, that people are putting their free time in it. Enthusiasm, because you want to succeed. And in our team, they all get the message, R&D is the nicest thing in the world. You make something what not was before. But it's also a bucket full of frustration. It's not all day hallelujah, because sometimes it's really not going to happen as you want to see. And you have to have a no-nonsense mentality. When you go in depth and say, okay, we follow the routes as it was in the past, it's not going to work. So that means also tradition is something in our company, skip it. We start with an open mind to it. So the improvement and innovation is really necessary, not only here for the development of electric car, but you will find it in all segments of the industry. And what we have achieved is, meanwhile, in the company, and they can tell about it, it's a Valhalla of technology. All the equipment for testing is in-house. The R&D team is reasonably small, but they have all the possibilities to do the testing, what is really necessary. And here, you come also to the team here in Eindhoven, actually doing itself in a larger group as what we are doing, but also they have to start from scratch. So that means you have to invent more or less your own things. So another thing is where it goes is here the activity and the competition on an international scale. Of course, that is in our field exactly the same. We have to do with the foreign markets up to in China and Korea. And of course, we are coming there, and that is always looking, that company is far ahead of it. So they're looking after this. And of course you get your competition because they want to do the same thing as what you're doing. And that is what we find here. Then the next thing is, of course, here also international, you have your competition with other universities. We have our competition generally in a lot of foreign countries, and that means also I have to train my students and R&D team also to handle the cultures we are working in. So then written sky high in our company, two slogans: we care and we solve. So if a customer comes with a problem, we will make it. At the moment we are working on a large project in the offshore industry in Norway. All the kinds of the R&D team have been in Norway to see what's going around and to help out, and even two are tomorrow back in the plane. We want to make the future a little bit better, and that means also that you have to have a look on the environment, you have to take a look on sustainability and so on, and that means that you have to put a lot of R&D in that. It's not that easy. You see also here with the cars, I think there possibly later on, when it comes to safety, there is something also to do. So, and of course, okay, we are not making any cars. We are also not making any things for the cars making more quicker or with more speed. But our thing is safety. And when this system comes to a development, also the safety of a car is important. Simple example are already the batteries. What we have done in the last couple of years is say, okay, is this world safe enough? And we come on many places and it is not really the case. And that means that we have taken a thing in the Achterhoek, and nobody expected that because it's a region where people go away and it's more or less getting into a rollator city. So what we want to do there is to invest in this region to get younger people to our city. That means we are going to build a campus, and that is going to build all the ceiling valley, and that is all for protective ceiling technologies. That is what's going to be in the Apple in Alton. So high tech on safety, and this is how it's going to look like. So actually yesterday we got the ground delivered from the city, so we start building now very rapidly. You see, this is a 45,000 square meter personal investment in safety. So that means we have pilot plans, we have education, we were organizing workshops. So, and hopefully in 2019 it will be fully in operation. So that is a step from 1973, where they started in a living room at home and coming now to a ceiling valley of many millions. And of course we hope that the students going around here are looking for an opportunity to go on that worldwide market, because again it's going from South Africa to Asia to Africa. It's every continent we are working in, and that's actually why we are sponsoring here also, to get people motivated to do that. Thank you very much.
For your kind words. Well, then of course we have built a race car, but what are we going to do with it? We want to compete in a Formula student competition that you see over here. And I would again like to emphasize the fact that all the people who are here tonight are supporting our team in a way to be a family, a partner or a friend, to make sure that our team members, our young engineers, have the chance to compete here. And of course, being able to compete here makes sure that you can apply your theory into practice and become a better engineer than you were yesterday. And that is also why our slogan is coming from, educating the engineers of the future. But eventually we want to win this competition, so now I'm going to tell you how. In this competition, you can gain 1,000 points for every event, like Formula Student in the Netherlands, that we are competing for the first time this year, because it's the first event in the Netherlands. You can get 1,000 points. And it is divided into several sub-events at such a race. So at first, there's the engineering design event. An event where you are able to explain to several professional juries of the automotive industry why your car is the best. How did you develop such a thing? Did you validate it? Did you make sure to take everything into account? And here you can get 150 points. Next to this, there's the cost event, where you have to explain to several judges how much does your car cost. You have to explain every nut, every bolt, every manufacturing. How did you make it and why did you make it so? And if you know how much your car will cost, then you also know how to sell it. And how to sell it, you can do at a business presentation. 75 points for that, where you have to make sure that the jury that is sitting there wants to invest in your company. Your company that is building Formula Student race cars and sell them, or in another way make money out of them. And this again emphasizes the fact that this competition is all about learning and about educating these engineers, not only in their own field, but also in fields like business, cost, and engineering design. So that is the static part of the competition. And now we can go to the actual racing, which is of course the most fun to watch. So first, the skid pad. A figure of 8 where the car will drive and you will estimate the best cornering velocity. How fast can your car go through a corner? And in Germany they make it even a bit crazier by making everything wet and making sure that you need rain tires to get as fast. And of course, the faster you are, the more points you get. After the skid pad, there's the acceleration. You have to accelerate your car from standstill for 75 meters as fast as possible. And as you see here, those cars accelerate very fast. They are even able to make the 75 meters within 4 seconds. This may seem very static to you, events where you're only driving around or driving in a straight. So luckily there's also the autocross, a race track which is kind of like a karting track, where your car will first in the autocross try to set a hot lap, a fastest time. After that there's also the endurance, where you are able to do 22 kilometers on the same track and see if your car, your prototype, can manage this racing environment for 22 kilometers. And afterwards, you also have an efficiency. How much energy did you use to go as fast as you did? Together, they form the final points of this circle. And here you can see the cars going around this track and see how fast they are. So, that is the formula. 1,000 points to gain in such a race. And of course we're going to do our very best to get to that 1,000 points in this season. But we need a car to race. And here to tell you everything about all the technology behind our newest racing car is my colleague, Torben Bernhard, powertrain engineer of University Racing Eindhoven.
year brings us right to where we are right now, here today. Then we're going to look ahead a bit to the upcoming months. What will we do? We will test. And then finally, the end goal, the race. So, the concept. We're going to stick to the concept of the URE10 and the URE11, which was derived with a lot of complicated calculations, and we still believe that this is the formula, the best formula for a formula student right now. Furthermore, our philosophy is that we do not want every component to be the best it is, or the best it can be, but we rather want all components together form the best system there is. So that's our philosophy in that. And in order to accomplish that, we decided to take the most design work that we can into our own hands. So we try to develop as many components as we can by ourselves. And that way we can fit them to our race car, to our application perfectly. Furthermore, this year we tried to focus more on the reliability of the car, and we tried to focus on gaining performance through testing. These aspects will come back in the design phase. So the design will start off with one of the most important components of the cars, the tires. The tires are the only thing that keep us in touch with the road, and all forces necessary to accelerate, to brake, or to go through a corner are transmitted through this small patch, which you see on the bottom. And the part of the tire that actually has contact with the road is not larger than the surface of a CD. So you can imagine that it is of absolute importance that we make very good use of this small surface. That's why it's already the 6th year that we developed these ourselves together with Vredestein. And so far we have tested through 14 different kinds of rubber and 3 different kinds of rain profile in order to get the best we can. The 10-inch tire will be the rim size of choice for this year, because it's very lightweight and we still can get the grip that we want. Furthermore, the key points of the tire development are obviously for a racing application. We want high grip. High grip means we can go through corners faster. And something very interesting is that we also focus in this design on a low working temperature. Because our races usually don't last that long, or at least they shouldn't, the tires don't have that much time to heat up, and we have to rely on having a huge amount of grip at low temperatures. So those are the focus points for the tires. Furthermore, to keep the tires in the great contact with the road at all times, we've developed our own double wishbone geometry suspension. This suspension makes sure that the tire is aligned with respect to the road as we want it to be in all circumstances, during acceleration, during braking, or during cornering. Furthermore, the goal of the year, reliability and performance to testing, can be found back in the adjustability of the suspension. I just messed up the order. Something cool about the suspension is that we're using Koni Formula 1 shock absorbers. And these dampers, these shock absorbers, are way lighter than any commercially available damper on the market, which will surely benefit our race car. Then, the adjustability thing. We use a front and rear roll stabilizer to influence the handling behavior of a vehicle. And we have adjustable anti-effects, ride height, camber and toe, and we focus them on being really easy to maintain, and in that way we can quickly change the behavior of our car to our own liking. Now, the tires, they are in good contact with the road. We made sure of that by our suspension. And something that you might know is that we can get more grip if we apply more vertical force on it. In order to increase this force at all times, we have developed an aerodynamic package. The aerodynamic package is basically like an airplane wing, but then upside down, meaning that the faster we travel, the more force is applied onto the wheels, the more we get sucked onto the road, basically. The aerodynamic package consists of 3 elements. We have a front wing, a midsection wing, and a rear wing. The rear wing is equipped with a DRS, a drag reduction system, which is also seen in Formula 1, for instance. And basically what it does is illustrated in the top two figures. We can open our rear wing, and by that we can reduce the frontal area, which you can see very clearly. And this reduces the aerodynamic drag by 80%. So that's definitely something that's beneficial to us. In the end, we redesigned our aerodynamic package. We tried to keep improving ourselves. And this year we were able to increase the downforce by 7.5%, so that's quite significant, while decreasing the weight with 20%. So that's basically a win-win. In the end, this downforce that is generated is 270 kilograms at top speed. Imagine our car weighs only 200 kilos, so that's quite a lot. And this 270 kilograms additional pressure we get on the wheels, but we do not have to accelerate this mass. This mass that is added is only 12 kilograms. So you can imagine that this process, this development is very efficient for us. It's very high performance. Something that we were focusing on as well is we took the midsection aerodynamics under a scope again, and we tried to improve the airflow through the radiator. The radiator is this thing which basically cools down our powertrain components, and by reshaping the shell, the duct that holds this radiator, we were able to increase the air that's flowing through the radiator by 50%. So now our car is even cooler. Well, we have our high grip tires, we have the suspension keeping it all in place, we have aerodynamics package which even puts more pressure on the wheels. So that means, in the end, we all do this because we want to deliver torque. The torque is delivered by our own custom motors, co-developed with AE Group. And the power of these motors is 30 kilowatts, or 41 horsepower. And yeah, this might not seem that much, but consider that they only weigh about 4 kilograms. So they are incredibly powerful for their weight, which is expressed in the power to weight ratio, which is about 10 horsepower per kilogram. Now this might not say that much to you as well, so we tried comparing it with some other motors, and we came up with the fact that a Formula 1 motor has a power density of about 5.9 horsepower per kilo. Now, I know that this is not actually very fair because we're comparing an electrical engine with a combustion engine, but still just to give you an idea how much power we were able to fit inside this small mass. We were able to do that because of their motor's high speed nature, meaning that they rotate at 18,000 rotations per minute. This means that every second they rotate 300 times. It's incredibly fast. And something very interesting, not very a little bit off topic, is that AE Group, the company we developed these motors with, they've published a paper about their development and their goals and how it was developed basically, and they won a prize for that, the best paper on ecological vehicles. So why am I telling you this? I want to show you that the bridge between racing and sustainability and durability is actually not that far away. It's actually quite close related to each other. Well, that having said, let's go back to our 18,000 RPMs. You can imagine that if we hook these motors up directly to the wheel, then our wheel will spin at a rate of 300 times a second, which is quite a bit too much if you ask me. That's why we need an in-wheel gear train. In-wheel gear train, yes. Now this gear train, the beauty about this concept is that on the one hand, it is able to reduce the speed to a speed that we find suitable for the wheels to turn at. And on the other hand, it increases the torque to 400 Newton meters on every wheel. So we have 400 Newton meters from these extremely light motors on every wheel. Something new we did this year is we looked at the gears and thought of ways to improve their functionality. So we came up with new manufacturing techniques. One is called super finishing. Super finishing is a technique that's also used in Formula One transmissions, and basically it makes the cars super smooth. So that's good for our efficiency. By that we can have more power left to transmit to the wheel. And after the gears are super finished, they are coated with a diamond-like carbon coating. Now, I don't think I need to tell you that this is an extremely hard coating, which increases the durability of the gears even more. So that's quite cool, if you ask me. Yeah, well, we have this four-wheel drivetrain. There comes another challenge that we have four motors, and we need to control them somehow. And the controlling is done well, in a sense, the first from the battery where the power comes from. The battery consists of 288 smaller batteries, which together form a battery pack of 400 volts and an energy capacity of 7.5 kilowatt hours. Now again, 7.5 kilowatt hours, what is that? It's enough energy to charge probably every phone in this room right now, about 3 times. So we could use it to do that, or we could use it to power one race car, which is also nice. Yeah, furthermore, something interesting, DC-AC. Before you ask, we're not starting any rock cover bands, or at least we thought of it. We already had a logo, which is nice, so... no, seriously, the DC-AC, DC is a kind of power that is provided from the battery. It's the kind of power that your mobile phone works on, or the kind of power that most kitchen utensils work on. However, not our motors, they are not kitchen utensils. Take care of that. So we need some kind of transformer, an inverter, a motor controller to transmit the DC to the AC, basically. Of course, we have 4 motors. That means we have to use a quad motor controller, which is also custom development together with ProDrive Technologies, also one of our biggest partners. So yeah, that finishes up the powertrain, which, as you can see, is complete self-development. So we're very proud of that. Yeah, to get back to the control part, we have these 4 individual motors, and that means that we also have to control them independently, right? Because the left motor might get some other torque than the right motor. And we thought about, yeah, you could install 4 torque pedals, 4 throttle pedals, but yeah, would not be that practical. So basically this offers us the possibility to make our car smart. We are writing some smart programs which can calculate how much torque to go to every motor in every situation. And this is, for instance, a torque factoring in combination with the traction control. Maybe the traction control is something that you have in your car as well. Torque factoring, most likely not, because it's over for a 4-wheel driven car. And the benefit of this is that we do not need a physical differential anymore. And we have the flexibility to calculate whatever we want. We can tell the car to do whatever we want and change it to our own liking. This is a very powerful aspect of the concept. Now these programs, of course, as you might know, they have to run on some kind of computer. So therefore, meet the DSpace Micro Autobox 2, which is a small but very powerful computer and essentially the brain of our car. And this computer gathers data from all kinds of sensors and actuators, and from that calculates what the car should do. Now, this is getting to be an incredibly complex network of sensors and wires and all that stuff, and that's why we try to keep it very simple, or we try to make it simple, with 2 CAN buses. It's a kind of communication system which is very reliable, very robust, very easy to use, and also lightweight. Furthermore, we added some I/O nodes. I/O nodes, input-output nodes. They are kind of mini computers that basically gather data locally and are able to actuate, I don't know, lights or buzzers or around the car. And they take the workload away from the DSpace and basically make it a simpler system. What you see here, by the way, is yeah, a part of the connector table, which Josh has been working on. And we looked into it, and it's just to show you how complex this really is. If we wanted to print all of these files at full scale, we would need about 160 pages of A4 paper. So that's actually quite a lot. And still, we would have to draw 225 meters of cable. Consider that our vehicle is only like 2 meters long, so that's actually quite a length. Well, something new we did as well is the system critical signals. Basically, we tried to improve the safety of our vehicle by making sure that every sensor is reliable, that we can trust every sensor. For instance, our battery holds 96 different temperature sensors, and once one of them only peaks for a very short period of time above a certain value, so indicating that one cell is maybe a little hot, then the car is able to shut itself down. So by that we try to think about safety as well. Well, we have got all these nice components, and to form a real car, obviously we have to fit them together. And that's where the chassis comes in. The chassis consists of two parts. On the larger part is the monocoque. It's a large shell of carbon fiber and honeycomb structure, and some reinforcements. And in the design of the chassis, we try to take into account the accessibility, manufacturability, and obviously we're still building a race car, so everything should be tightly packaged. The accessibility thing can be seen in the top figure, where we showed the URE11 and the URE12 monocoque side by side. Now you won't see that much of differences, only the maintenance hole in the front. This maintenance hole in the front of the URE11 was quite small, and you could only slide one hand through, and this made it very, very difficult to maintain the car and to adjust things. That's why we just made it larger at the cost of a little bit of weight. In order to improve the maintainability. And now it even is so large that you can just stick your head inside. I don't know if that's necessary, but please don't do it once it's revealed. Furthermore, the handmade carbon fiber and honeycomb monocoque. It's handmade. It's one of many parts that we make ourselves in the workshop, but this component is definitely the largest and most difficult and time-consuming. And it's a real challenge to construct such a thing. This monocoque, it contains the blood, the sweat, the tears, but mostly frustrations of every team member we have. By using a new material and redesigning the composition of the monocoque, we were able to decrease the weight by 1 kilogram to the weight of 15.4 kilograms. This is not that heavy for a chassis of a vehicle, you know. Furthermore, I just introduced the roll hoops. So if we go that fast through a corner, then the car might roll over, then at least we have some protection for the driver's head, which is nice. So no problems there, everything fine. Good. Well, these components together form the URE12. 190 kilograms, a lot of power, a lot of torque, and this combination enables us to go in 2.3 seconds from standstill to 100 kilometers an hour. This is also, the cornering abilities are mainly improved by the downforce from our aerodynamic package, which is about 60 kilogram at 60 kilometers an hour, and as I mentioned, at top speed it is even 270 kilos. We did this with custom developed tires, with double wishbone suspension, full aerodynamic package, our four-wheel driven powertrain, a CAN system, and everything packed neatly inside of a carbon fiber monocoque. Well, that's it, basically. That brings us to where we are right now. Production. We tried to, most of you might recognize this art style. We tried to make an IKEA-like inventory list, you know, the one with all the components and the number of components that are inside, and we quite quickly find out that we had to do this with over 5,000 components. So yeah, then we were like, nah. So we didn't do that, but we want you to know that it's one of the biggest challenges to get every single one of these components at the right time, at the right place, ready in a good state to be assembled, to be post-processed, whatever, and even consider that we have only a few months to do this. So this is one of the biggest challenges in the whole year. To better show you how this production phase went, we made a small video. Okay, so the URE12 is produced, it's assembled, it's ready, and it's here. Ladies and gentlemen, it's my honor to first talk about testing a bit more. I'm sorry, you'll just have to listen to me for a few minutes. So the next few months we'll focus on testing. The URE12 is ready, so in order to prepare it fully for the races, we'll try to make as many kilometers as we can, testing its reliability, its robustness. But furthermore, we also want to improve the performance, right? So we want to gather as much data as we can. We want to see how the vehicle behaves. We want to get to know it. And if we know it, then we can improve it. Furthermore, this data is also very, very important for us because it helps us to make better models of this vehicle. And with these models, we can quickly design and simulate new race cars. Furthermore, something very good to do is the driver training. It's very important because these race cars, they don't act like a normal car, they don't act like a kart. You can't actually compare it to anything specific. So it takes quite some time for the driver to get used to them, and that's why that's also a big focus point. These testing phase will be mainly executed by the vehicle dynamics department and the control department, and obviously the testing department. But don't think that these guys did nothing until now, just waiting for the 12 to be finished. With the URE11, we tested 412 kilometers, which might not sound that much for you guys, but actually for us it is, because we make these cars to last about 2,000 kilometers, so it's actually quite a bite out of its lifetime. And to give you a comparison, 412 kilometers is about 15 race weekends. So we kind of simulated 15 races, of which we will only attend 3 in the summer. So we gathered a lot of useful data and knowledge from that. But not all testing happens on the vehicle, right? So these are driving tests on a closed terrain where we can test the full car. But we also want to test smaller components. On the left, we see a very happy chassis manager testing the suspension rod strength. It seems to me that there is about 350 kilos of weight hanging on just one single piece of carbon fiber. Even right now, he's looking very happy. Okay. Well, as you can see, the test was passed, so that's nice. Our vehicle won't break down in the first corner. At least I hope so. On the right, we see our motor test bench. This is also something that we want to do more right now, is by using this test bench where we have 2 motors, one on the left, one on the right, the black things. By using this test bench, we can measure certain properties of these motors. And if we know these properties, if we know these parameters, then we can be able to get more power out of them. Or we can be able to know its weak points or its strong points, or where to improve a second version, for instance. So it's very important to test all this. Now, once the testing is done, it's ready for races. And Jesse also already introduced you to the organization of the races and the technical challenges. But I've talked enough about technology. I don't want to end this presentation with technical stuff. So I want to tell you a small story about Formula Student, and what I feel is the essence, is what we are all doing it for. Let's start. When I started my academic career at the age of 4 in kindergarten, I was placed in a group with all kinds of different kids from the neighborhood, and we had we had fun playing together, but we were kind of different personalities with different interests. And it wasn't until mid-school that I was a bit more sorted towards the people that of my own level, of my own capabilities. But still, we had very different interests. And at the age of 15, I was able to choose. I was able to specialize myself into more science and technology related parts, subjects. And the kind of peers kept expanding. When I joined when I started studying here in Eindhoven at the University of Technology, suddenly people from all over the Netherlands met there. Students like myself who are ambitious, who have a passion for technology, a passion to create and innovate. And then I joined URE. My peers of kindergarten toddlers have made place for a team of ambitious students who, like me, who like myself, love race cars, and with the capability to design such complex systems and the desire to innovate. It is truly remarkable how from all of these guys in the Netherlands, we have found each other here with the same interests, with the same skills, with the same goal. And imagine now that this summer we are going to race. We are going to race and we are going to meet thousands of engineers just like ourselves. Engineers from all over the world. We are going to meet the Spanish versions, the Indians, the Brazilian, the Russian versions of ourselves. And on these races, we are going to teach them what we know, and we are going to learn from them what they created. We are going to share culture, we're going to share ideas, we're going to share experience. And that, for me, is the very essence of Formula Student. I think it's time, Jesse.
So, yeah, thank you very much for these words. I think everyone in this team feels the same way. So I would now like to invite the team to gradually spread themselves on the left and the right side of those two doors. Thank you very much for your attention tonight. Please enjoy your drink, stay and look around at the car, and have a good evening.
beautiful.